very limited or narrow range of the elasticity. So basically, you simply give a slight kick, then that material will get into plasticity. And right away is the energy will be absorbed. If that material has any defect, then the crack will propagate easily and get until the fracture. But compared to the ductile material is more, I would say, stronger than accepting the loading. Probably that time you haven't born yet. 1989, 1987, I forgot. There's during one launch of the space shuttle, and it just exploded, I think, within a few minutes after launching. Do you remember that story?
Challenger?
I forgot which one. And happened in 1980s, probably 87 or 86, whatever. Probably that is before you born, right? Most of you were born here.
Yeah, it was like there's like a thermocouple failure at the end.
Not thermocouple.
It was an O-ring.
It's an O-ring. That is the due to the fuel leak through the O-ring. Why? Because the O-ring under the very extreme low temperatures, O-ring, although it's rubber, but under that low temperature, basically it's become like glass. We call the glass-like material. Become the glass, so basically the O-ring losing its capacity to prevent the kind of leakage. So the fuel leaked from there, then they got ignitions by the fire, and they just explode during the air. And that is the one quick example for this. And that is, more information will be about the material science, and that is called the glass transition temperature, about this kind of material. That's a different story. We don't need to consider that one. So let me move on this quickly. Basically, those are the material properties. So this one, compute the delta equal to PL over EA. Sometimes the people like to use F. Okay, some depends on the symbol you use. Sometimes people use F. So delta equal to FL over EA. Don't feel surprised. This is the equation. We can apply this equation to many scenarios, and the follow-up is the application of this equation. For example, we might be able to apply that basic, I would say this is a generic form, or this is a template, to apply to different material models. For example, the first case I'm showing is the non-homogeneous material. What we call the non-homogeneous, that means the cross-section is varying from one place to another. We call the non-homogeneous. If we call the homogeneous, that means that everything is uniform, everything is the same. So for this case, how can we calculate? I will get that out. So maybe let me utilize these slides and then write down some words. So for example, for this case, let me call this is the A. This is fixed against the wall. And let me call this end is B. And in between, let me say this is C, D, etc. Okay? So for example, we want to calculate deformation between B and A. So that means I want to calculate what is the deformation of the total this non-uniform bars. So for this example, we can calculate is this. Deformation B relative to A, that is, for example, this, let me call this is B1, okay? So B deformation, B relative to B1, and then deformation B1 relative to something, and then something until deformation of C relative to A. So that means this part is the deformation of this case. And this part is, if I take this as the material models, then this part simply is the deformations of this one. So simply the technique is this, which simply is to we do the piecewise calculations. Okay, that is the strategy. And to do the piecewise, again, let me, right now to make these things easier, let me take away all the unnecessary drawing here. So for this case, this would be, I think maybe that would be easier, can allow me to rewrite this. So to cope with the sequence of this one, why not let me rewrite this one. So B relative to A will be equal to this one, B relative to B1, and then plus continue plus delta D relative to C plus delta C relative to A. Okay, so I think allow me to erase this one. So in this way, that is the piece by piece, the comparing, that will be easier to kind of mentally work on the things, okay? And actually this one is, for this case, you can see, right now we take the free body diagram is this. We take the free body diagram for this piece. This is B, this is B1. And then continue, we take the free body diagram on CD. And then also we take the free body diagram on DA. CA, thank you. And then you can see right now I want to utilize is our generic model. For our generic model, we only have is one uniform material bar. So to utilize that equation, I must come up with a drawing of the free body diagram that fit into that material model so we can utilize this equation. So for this example, I pick this as the one free body diagram which is here. And then gradually I work on the individual pieces. I try to find out the uniform, the basic material model that can fit into that case. You know what I mean? That is a material model. Then we analyze the force. The P applied to here, that is a given. And in these serial connections, by taking up the force equilibrium, let me use the color. This is the action-reaction force on this side, and this is P. And again, in each piece across the interface, the P, the reaction will be transmitted. So on this case, here will be P, and here is P. And reaction, action, reaction, this is P, and this is P. Am I right? If you look at individually, this is the material model we're fitting into our basic definitions. For this, that is another one. And for this, that is another one. So that means B relative to B1, that is coming from here, basically that is P L over EA. Take up our geometry, take up our formulas, and this one is pertaining to this material. For example, say if this has the length, whatever the length, whatever the Young's modulus, whatever the area, so let me call this is for the portion BB1. So that means here, what I mean is we have to take up whatever the information are given in this problem in this segment. And that is the meaning of this symbol. Okay? And then the same thing for this one, that is PL over EA. and for whatever the information in this piece, and that piece is CD. And then in this case, this is the portion for this one, that is PL over EA, for whatever the information that is AC.
How come the last one's not V1 V?
Huh?
How come the last one's not V1 V?
Oh, either way. Just label it. You know what it means. Okay, doesn't matter. Yes.
Since we're compressing all those, will we have a negative delta?
Yes. For this example, that is a magnitude, and in total, that is compressive. Okay, so in general, for this case, is this, we write it up, is this, based upon this information, this is B relative to A, that is the summation of the piecewise calculation. For each piece, we still stick with our generic platform here. So in general, for this case, we simply have the more general equation is this. For each piece from I to 1 to N, that is the label of PL over EA. For each segment, we simply take out the individual terms, we take the sum together. And more practice will be on using these equations. And again, I wouldn't say this is a formula, okay, just provide you kind of symbolic calculation. The only formula is that one. And how to apply to this, and we can use the example C if I can let me work on this one first, and then we'll go back to the different scenario. Do you need me to turn on the light? Would that be okay working on this? Okay. So for this case, we have a loading like this. And here we have the uniform, actually two pieces of the different size of the bars. And then we want to calculate is the deformation of this. This is made of steel. So basically what we want is to find out what is the displacement at this free end, because this is fixed, so the deformation of the system can be represented by the displacement at this point. So let me label this is A, this is B, this is C, this is D. So basically for this case, that means we calculate delta to calculate the displacement at D, or to calculate this deformation D relative to A. Either statement are equivalent. Displacement is the movement of one point from one place to the other. Deformation is the change in the dimension of the whole materials. So hopefully you can understand the difference between the terminologies. Let me kind of peek because I couldn't memorize my slides, so many, and I know some lecturers, some instructors are very good in memorizing what they're going to do in the next one. I couldn't. To be honest with you, I couldn't. So for this one, again, we try to stick our concept to this formula. We try, by all means, to make the free body diagrams, multiple free body diagrams, to dissect or bisect, put this model into a few pieces. Each piece fit into that generic formula. Okay, so let me erase this one. And let me copy this one, because I'm going to turn off this slide. I'm going to give myself more working space.
switched your labeling.
Huh?
Oh, that's for the other file, never mind.
Oh. Let me try to figure out all the, put out all the necessary information. 618 square. Okay, so I can turn off this one a little bit. So let me turn on the lights. So this is our problem, and our goal is fit into that one. Our generic model is this. Let me write it up. Our generic model is this. This is the force, P, and that on the uniform material, which means EA and L. Then our formula is PL over EF for this segment. We stick with this generic, and I'm going to do something for here. You can see across the two bars, I'm going to put into the segments. How many segments? 1, 2, and 3. Because in this segment, if you know the statics pretty well, or you can quickly do it, you can see the reaction force in this segment is different from here in general, and could be different from here.
So you're going to have two tangent forces combining with a...
I'm going to do it now, and although I do this for many years, I still couldn't memorize the numbers. Otherwise, we shouldn't be the engineering, right? So again, here I showed you a tip is this. How to make the selection of the needed segments. One is to choose wherever the geometry is not uniform, choose from that cross-section, from that interface. The other one is to even take cut on where the loading is applied. Okay, so from here, let me calculate first the distribution of the loading. So for example, here, let me label carefully with the locations, okay? So this is the reactions in each piece of the segment. And what you can do is this. I'm going to gradually build it up. And for example, if say initially probably I think in your static you have learned the force diagram, or called the shear force diagram. Is that right? Yes, right. Only two people nod your head, but let me do it one more time. So for example, to do this, for example, you can choose a cross section, pick up any cross section. And now the goal is I want to analyze what is the reaction in this piece. Okay, so that is my goal. So I can do on the scratch paper here. So let me pick the right hand side. So this is 75. And 45. Let me copy the information first. Sorry to make one person bored. So that is the case. And now I want to calculate what is the reaction here. We simply take the force equilibrium. 75 plus 30 is 105, minus 45 is 60. So that means here must be 60 force, right here. Okay, the 60 is the force. And how could we label the force here? The 60 you should use is this. Not to use the 60 pointing to the left. No, the 60 is going to stretch. So the sign convention here I would like to use is this. Positive for stretching, and negative for shorten the material. Okay, that is a little bit different from what you learned.